And hello everyone, welcome back to our discussion on large eddy simulation models. In the last video, we were talking about using a characteristic length called delta to sort of filter our equations. And remember, filtering is just a very complex way of saying we want some weighted average of a quantity, for example, like a velocity. So we have that weighted average. Where was it? Yes, this is what it looks like, the weighted average, using some function gr. Okay, using some function gr, and in general, gr can be a function of r and x, meaning it can vary with space. Okay, but of course, for simplicity's sake, we like to just assume it does not vary with space. And yeah, but it can. Okay, so but for now, we just simplify it so that we use the uniform gr across all the whole space. Okay, so after that you do this averaging process. At least in theory, you will have the velocity decomposed into a u bar plus u prime, right? Your velocity will be decomposed into the filtered velocity. This is the filtered velocity I'm highlighting. And of course, this is the residual. Now, step 2, after you've done your filtering process, you pretty much substitute back into the equation. Oh yes, one more question I have not answered. How do you get this characteristic length? Okay, so how to get delta, the characteristic length, the characteristic length scale, or filter length scale. Delta, okay, this is a pretty one of the easiest ways to get delta. There's one simple way. In some CFD codes, for example OpenFOAM, delta is simply the cube root of the cell volume. Okay, cell volume to the 1/3 power. That will give you some characteristic length scale. Of course, if your cell volume is changing throughout the grid, for example, close to the surface you have very fine grid, a very fine small cell volume, then you will have a smaller delta towards the surfaces, right? So normally, let's say you have a surface far away from the surface, the grid is pretty coarse, but closer to the surface, the mesh becomes finer and finer. Okay, the mesh becomes finer and finer, so your delta becomes smaller. This is the reality of it, and that will actually make this it will make g actually not just a function of r, but a function of x as well. It's a function of position, because far away from the cell wall, from the boundary, you have a very large mesh, so delta kind of changes. Close to the surface, delta becomes smaller, and so that your g will change. This filtering function, or this averaging thing I'm talking about, is a filtering kind of a function. Okay, so that's the thing to get a weighted average. Or you can specify it manually. You can specify it. You can specify it manually as well. But this is how some of the code solvers solve it. Of course, if you have a uniform cell volume throughout your mesh, then delta, your G will become independent of it will become independent of, let's say, what do you call that? Yeah, independent of wherever you are in the grid, wherever you are in the mesh. So, okay, step 2, after getting u into u bar plus u prime. Okay, after filtering, so we did the averaging process over space, for example, for large eddy simulation. Okay, so this is one of the most common ways to do large eddy simulation filtering. It's through space filtering. So you pretty much get the same thing. Okay, you have u equals u bar plus u prime, and as always, we try and substitute all of this back into our relevant equations. So for Reynolds average Navier Stokes, we have this kind of form where we substitute the average velocity into this continuity equation, which is of course incompressible. This is the incompressible version. And of course, for Reynolds average Navier Stokes, we also substitute this into our momentum equation. However, there is some difference for large eddy simulation filtering, okay? Because actually, when you have your momentum equations, you will have this u squared term, which you will need to sort of do an average. All right. So when you expand this out in Reynolds average Navier Stokes, so u squared equals to u bar plus u prime, and here it's the time average velocity. This is the fluctuating bit with time, not with space. So you'll get this kind of thing. All right. Now, if you take an average value of this, of u squared, you would actually just be expanding. You just take an average of this expansion. So u squared, it is constant with time. U bar squared is constant with time because u bar is constant with time, more or less. Okay. So u bar u prime is also, is changing with time, but the average, because you can take this u bar out. U bar is a constant with time. You will just get the average of u prime. Average of u prime is 0. That's why this term disappears. I hope you are quite familiar with this. Have you done a Reynolds average Navier Stokes before? And u prime squared, that is non-zero, so that remains. Okay. So when we substitute all of this back, we will get this kind of equation here. All right. So yeah, that's what we get. We substitute this back into the momentum equation, we'll get this. All right. And of course, we have to combine it with the continuity equation to get some simplification, but hopefully you know already. All right, so what about the LES filtering? So just ignore what that one is. So you have the mass conservation, partial u partial x plus partial v partial y plus partial w partial z equals 0. Or one very short-handed way of writing is partial ui partial xi equals to 0. Now, whenever you see this notation, this is actually a truncated version of this. So when I write something like this, I'm meaning, okay, I equals 1, 2, and 3. Or yeah, I equals 1, 2, and 3. So what I'm saying here, this is, when I do this, I actually mean, this is called Einstein notation, by the way. Equals 1, 2, 3, partial ui partial xi. All right. So this is just introducing Einstein notation to you. 1, 2, 3. Alright, u1, x1, u2, x2, and u3, x3. So this can be representing the x direction, this one is the y direction, this one is the z direction, where 1 is the x direction, 2 is the y direction, x3 is the z direction. Hopefully this can get used to this notation, because it will shorten a lot of the ways we write. So this is a little introduction to Einstein notation. So bear with me when I use this, all right? So I will keep going through it until it's like more familiar. So this is Einstein notation I'm using. It's a lot easier to write it like that, because it kind of shorthands all of this, because there's so many terms. So I just truncate it for neatness. All right. So you have this partial ui partial xi equals 0, which means I'm just doing it in x, y, and z direction. And of course, I will say ui equals ui bar plus ui prime. So this is true for x, y, and z direction. Okay. All right. I am not this time. I'm not summing it up for together. I'm not summing it up together, right? X, y, and z direction. So this is what it means. I will have one of these equations for each, of course. So now I substitute this in. All right. I'll just copy and paste this here. All right, and then of course when we do that, we will just have two terms. Okay. So one term is this, and one term is this. This one is the non-filtered part of the velocity. Okay. But one assumption is this. grx equals to gr. What I mean is that the filtering function, remember I was talking about the filtering function, this gr, it can be a box, it can be a Gaussian distribution. It doesn't change with the box filter, or the filter doesn't change with doesn't change with what do you call that? Yeah, it doesn't change with distance. Okay, so yeah, the filter doesn't change with distance. So what we can say is this: if filter doesn't change with distance, then we will have a more or less uniform distribution of turbulence. So remember, this is a summation of the residual velocities of u prime for the x direction, y direction, and z direction. So remember this summation. Yeah. So this is actually, okay, I'll just write it down again. All right, this is UL1, 2, and 3. Okay, so if we have a constant filter, we can make more or less like this assumption that this filtering process is such that your net turbulence, your net residual velocities as a function of x, u prime. So there will be residual velocity in x, y, and z direction. So if your filter is the same, we assume that they all cancel out. you know, on the whole. So they cancel out on the whole, and therefore we were left out with this. So yeah, we can assume this because our filter doesn't change with distance. Of course, if it does, then it'll be slightly different, but for simplicity's sake, we do this. Okay, yeah. So we have this equation, and of course this equation as well. All right. Then next we have to move to our momentum equation. Okay. So the filtered momentum equation is as such. Okay, I'm going to type this out. This is from this is from the, what do you call it? The book I was talking about, the Turbulence book. It is Turbulent Flows by Stephen V. Pope. This equation came from there. I mean, it's not his. I mean, it's from his book, but it's not his specifically. Okay. And anyway, let me just write that out for you. Okay. All right. Partial xi is just partial xi squared. Okay. Okay, so this time, instead of seeing just one I or one j, now you have I and j both in the same equation. So what is this actually? Well, if we take a look, we can take a look at our Rand's equation for comparison. So where are these terms? Okay, just ignore the closure terms for now. These are Reynolds stress terms. Okay, so this one is the time varying part. Okay, this one is the convexing part, because you see a del x, del y, and del z part. You have a pressure term here. Okay, it only appears once in each equation. Then you have this, which you see a divergence term over here. All right, so what does this actually mean? Okay, we can carry on like so. So let's expand the i's out. Okay, so we will have plus plus. I'll just expand the i's out. u1, i1, u2, x2, u3, x3. Okay, and then I will expand the viscosity term out as well. Or the, yeah. Okay. So this is from I equals 1 to 3 because there are 3 dimensions. x2, x2, x3, x3. Now, just pay some attention there. Okay, I think I forgot to do bar on this one. uj, bar, bar, and bar. Okay, so now this is substituting into the filtered equation. All right, so if we substitute this expression into our Reynolds average Navier Stokes, and we do some simplification. I'm not going to write that all out here. It's a bit complex, but hopefully you get the concept. You get roughly the concept of what's going on. So when you see this equation in this form, what you're seeing, all right, you have a uj, u1 uj, u2 uj, u3 uj, okay, and then you have a uj differentiated across 3 directions. You can see if you just do a quick comparison, this term I'm highlighting is actually just this term, which is the divergence of u bar. Okay, so this is of course the time derivative term. This term is can be sort of linked or related to this convective term, but of course there are other things going on here. There will be closure terms that you don't see at the moment. And of course this is our pressure term, which is directly analogous to this. Why is there a uj here? Because there is 3 momentum directions. J represents 3 directions. Okay, 3 equations for velocity vector in x, y, z direction. Okay, so this is a Cartesian coordinate direction. So uj is just meaning to say, okay, I have to copy this equation 2 more times. One for the x direction, one for the y direction, one for the z direction. So x direction will have its own, y direction will have its own, and z direction will have its own. So you can imagine so much complicated equations to write out. I'm not going to write them out. Instead, I will use this truncated short form, the shorthand Einstein notation of writing is, okay, so I will have a uj. Every time you see a j, meaning to say I'm going to copy and paste this this whole equation 3 times. And this I means, okay, just now what I meant, the summation I'm talking about, like over here, this is Einstein notation. So every time you see this, just try to get used to this notation, because that's going to help. A lot of textbooks like to use Einstein notation, especially this textbook. But yeah, so this is what it's talking about. When you expand this small little equation out, you will have these 3 large equations here. Okay. Of course, I'm supposed to change this x direction into j equals 1. Okay, sub j equals 1. This y direction, substitute j equals 2. And z direction, substitute j equals 3. Okay, so x3 is z, x2 is y, x1 is x. Okay, so that's all we are doing here. Now, problem comes when we try to expand this uj term out. Okay, so remember in the Reynolds average Navier Stokes equation, we have all these closure terms. Where does the closure term come from? Closure terms come from this. Okay, they come from the convective term, the convection term. This is a momentum convection. Okay. Alright, so you try and expand this out. Alright, so this is what I did just now, before. We can expand out using the filtered quantities. Again, we have ui and uj. And then we'll get something rather complicated. Okay. We have ui uj, where ui equals to ui bar plus ui prime, uj equals to uj bar plus uj prime. Multiply them together, and then you'll expand it out as you get. So you have u bar I, uj, u bar j into ui prime, u bar I into uj prime. Yeah, you get this product basically. And then you try to do the averaging, because we wanted to find this quantity, right? We want to find ui uj bar. Okay, so to find ui uj bar, we do this, we just expand out. But however, you got to note that this filtering process, okay, when we do a ui uj bar, we need to filter again. So remember what's the filtering process? The filtering process is this, right? We go through this complicated G equation thingy. All right. So instead, I want a u bar uj, ui uj bar. Then I will just substitute this thing here. Okay. Okay, I should use this instead. Yeah, there you go. Yeah, so ui uj is a product, and you just do this whole filtering thing again. However, you cannot assume that every term disappears here, because while this term is constant, I mean, in the time averaging sense, u bar is constant, but in the space averaging sense, it is not constant. So we cannot just assume that if you filter something twice, these terms disappear. They will stay. Okay, so these terms will stay, as well as these terms. Okay, so definitely there will be a difference between, okay, the final form and what we have now. So what we have now is this. Okay, what we have now is this, and what we kind of want at the end of the day is to have something like this that kind of resembles our Navier-Stokes equation. U I bar U J bar. So we have this is what the Navier-Stokes equation will look like, but there's extra terms. So this is the filtered Navier-Stokes equation plus some extra term. Okay, what is that extra term? These extra terms are actually the closure terms that we are talking about here. All right. So what does it look like at the end of the day? In the end of the day, we have something like this. Overall, del u bar I plus del x over del xi. Okay, so remember this is Einstein notation. Likewise, this is also Einstein notation. So you have a filtered velocity term where we use this yeah, okay, never mind, just pay attention to equation 13.95. This is again from the same book. All right, so yeah, eventually you have this and this two. Okay, this two will, and what I mean, why do we want to form it like this? Because this is actually the Navier-Stokes, and I mean, it looks like a filtered Navier-Stokes equation similar to our Reynolds average Navier-Stokes, and we have some extra term over here. Okay, yeah, okay, and yeah, you have this Navier-Stokes looking like term here. Now if you apply the product rule to this, and you will find that yeah, there will be a lot of terms, but again you have to combine it with this. Okay, so first use product rule on this term, which will give you uj bar partial u I bar partial x I plus u I bar partial u j partial x I. So nice thing, okay, there's one more thing here. I need to filter that velocity. Yeah, nice thing about this Einstein notation is that when you do this chain rule thing, it kind of shortens your pin a little bit. So instead of writing everything out, you just have to do this chain rule thing once. It will work already. So and we have this thing here, this from the continuity equation, partial u I bar partial xi equals to 0. Then we will have this. So this is 0. And this is all that remains. Alright. So with a continuity equation, we can like get rid of this term. And therefore, yeah, just make sure, yeah. Alright, I'll get to the extra term part in a little bit. Therefore, we have this. So this looks really much like the Reynolds average Navier Stokes, except it's for filtered velocity. Now, what about the link between this UI uj bar, this? What about this and this? Alright, so this is where you get your extra term from. I will talk about it more in the next video. And of course, I know I didn't quite explain the whole substitution of UI uj into this equation and filtering the Navier-Stokes equation. Kind of skip that part because that's very, very long. But yeah, I mean, that's what we are conceptually doing, and that's how we arrive at this equation. Just I'm truncating the explanation so that we can speed things up a bit. If not, it'll take a very long time. But hopefully that doesn't subtract from the qualitative, knowing what's going on with the Navier-Stokes equation and what's going on with LES filtering. So I'll stop here. Thanks for watching. I'll see you guys again. Bye bye.